Okay, the fact that functional lateralization is a salient feature of human brains organization has been known for a long time, at least from the time of Broca. However, despite a long history of research in the topic, there are still many uncharted territories. So first of all, taxonomy of lateralized functions is still missing. Secondly, quantitative models of how functional lateralization is organized is also quite sparse, by which I mean that we don't have sufficient knowledge of whether there is a similarity in a diverse family of lateralization patterns which brain can reveal to us. And also, the mechanism of its emergence is also quite unclear, because I can single out two broad views on its emergence. One is that functional lateralization results from a decrease of callosal function, possibly related to the expansion of human brain during evolution and the increase of conduction delay between two hemispheres. And therefore, maybe it could be efficient processing. A good idea to have a process in one hemisphere as a result of it. And the other view on it is that actually functional lateralization may emerge from interhemispheric competition. It actually have slightly different prediction for callosal connectivity, because you need a good counterbalance in between the working of hemisphere. So maybe you need a better connectivity. So in our study, we aim to bring some or add some clarity to all these issues, or to all of these issues by attempting to produce a comprehensive map of brain lateralization function, then examine the relationship of lateralized regions to corpus callosal connectivity, and also characterize its low-dimensional architecture. Well, it's easier to be said than done, because you can possibly scan participants for all functions, cognitive functions you want to. Therefore, our trick was to use neuroscience meta-analytic maps to do so. And we did it in combination with highest quality diffusion data from Human Connectome project. I'm not going to describe in details what neuroscience is about. It's well known in the neuroscientific community. I only mention facts which are most relevant for our analysis. First of all, it's a huge database, but not all maps, term maps there are useful. And therefore, we start our study with curating them and selecting only those maps which we thought may somehow pertain to cognitive functions. Some examples you can see in a table. Secondly, these maps are not given symmetrical space, and anatomical asymmetry is a well-known fact. And so we start preprocessing with registering our maps to symmetrical MNI space, and then we calculated the right-left difference to get term lateralization maps. Also, what transpires from this table is that some terms in the database may be just trivially related, like plural or singular forms of the same term. Therefore, we perform dimensionality reduction using very max rotated principal component, gives us component loadings for each component, and then we regress out the component loading matrix onto original term maps to get component special maps. And then we perform permutation test to get statistically significant lateralization maps. We end up with 25 functional lateralized regions. Here they're all shown, and the labels are the terms which had the highest loading along this component. Some of them obviously are not surprising, like language component with Wernicke and Broca area lateralized in left hemisphere, and contralateral lateralization in cerebellum. Then we wanted to see whether these regions, which we just identified, have a different callosal connectivity comparing to regions which are non-lateralized. And to do so, we perform spherical granulation tractography on 70 diffusion-weighted data. We then transform this tractography to normalized space, and then we seeded tractography from non-lateralized voxels and lateralized voxels to corpus callosum to get a left-right probability map, where probability is given as a occurrence of connection across sample. I haven't mentioned how we define non-lateralized voxel regions, but effectively it's the same procedure as for lateralized regions. The only difference, the input to our pipeline, which I showed previously, were the left and right hemispheres, not the difference between left and right hemispheres. This gives us a macrostructural measure of connectivity, but also we wanted to look at the microstructural connectivity. Sorry, I forgot to mention that before talking about microstructural, we then perform sampling from lateralized and non-lateralized regions with subsample subset of voxels, and each time calculating the difference between two to construct the distribution of the differences between two sets of voxels. So macrostructural connectivity, we obtain axonal water fraction maps using from the same set of the data. We then average them and mask out the midsection of corpus callosum and perform with pretty much same sampling as for macrostructural connectivity to see the difference between lateralized and non-lateralized voxels. So that's the example of how average, at the above it's actually the representative subject in our sample, it's callosal connectivity, whereas the middle row are the probability of connection across the whole cortex, which has some similar features to histological maps acquired from the monkey studies. And when we look at the differences between lateralized and non-lateralized region with respect to callosal connectivity, here the red is the difference between in the right hemisphere and the blue in the left hemisphere. You only observe the difference for macrostructural connectivity. You see the whole distribution shifted to the negative values, meaning that in macrostructural connectivity, lateralized regions are less connected to the corpus callosum, whereas there was no difference in macrostructural connectivity. However, we thought maybe that within the pool of lateralized regions only, the strength of lateralization can be related somehow to the measure of macrostructural connectivity. It indeed was negatively related. In other words, regions showing a greater strength of lateralization also show a proportionally reduced macrostructural connectivity. Finally, we ended up characterizing low-dimensional architecture of functional lateralization in the brain. To do so, we took our lateralization maps, calculated pairwise correlation between each of them to get a similarity matrix, and then use a spectral embedding and to observe low-dimensional organization of these maps. And if you look at the first three dimensions, which is here the examples of flat projections of each pair of dimensions, so you can see quite distinct triangle organization, and we were quite excited about it because triangular organization is unknown in evolutionary biology, and because they are related to the concept is known as Pareto optimality. What it means is that in reality, in biology, you can fly high, you can run quickly and swim quickly simultaneously. There's always a trade-off between traits. And so triangle organization essentially is a representative of these traits. And because it's an important concept there is also the test for testing triangularity of the organizations. Say if you have some data distribution on the right, you can fit convex hull and triangle with the minimum areas and observe how different the areas is. And if it's a area is not too, the difference is not too big as in our case, then the convex hull is actually is a triangle. And you can do just then generate random maps and see whether the difference is not just by chance. And as a result, we observe that the triangle organization preserves in 3 dimensions. In other words, our triangle has 4 vertices. So if we zoom into this figure. So you can see that at the vertices you find clusters of terms which are semantically similar or maybe functionally related. It's a decision-making, emotion, action, and language. Furthermore, you may ask what actually situated at the vertex of this triangle. In other words, what are the canonical patterns or archetypes of functional lateralization? And the easiest way you can do this is just regress out the voxels in the terms on the coordinate in each dimension, and then evaluate the vertices. And here we present canonical patterns for each of these traits or archetypes of functional lateralization. Pretty much expected. You got a symbolic communication straight with left lateralization of Wernicke and Broca area. Perception action is right lateralized in the frontoparietal regions known to be implicating special attention, emotion. Emotion is a right lateralization areas known to be involved in mirror system, and decision-making canonical maps has a dominant right lateralization frontal region. These findings we think is a report for the first time. Okay, so summary findings. We identified 25 lateralized functions in the brain. We identified 4 canonical axes for the whole set of lateralized functions: symbolic communication, emotion, perception, action, and decision making. And lateralized areas showed a decreased callosal connectivity. Thank you. And sorry, I forgot to mention of the acknowledgements. I did this work while being in BCB lab in Paris with Michel Thibault-Deschot and Maurice Carbetta. And if you're interested in further details, please refer to paper as published, and please come to the poster for further discussion. Thank you.